Welcome to Biogas Basics. My name is Jürgen Kuber, and today's presentation is about the optimization of three-stage membrane-based biogas upgraders. These upgraders are common in the UK biogas industry because of their plug-and-play nature and low visual impact. They have several process variables that can be used for process control and process optimization. The results shown here can offer some easy wins to existing membrane-based upgraders. Check the publication listed below for details. In this presentation, I'll keep the maths to a minimum. Let's start with the mass balance of a countercurrent membrane module. The module has a feed inlet and a retentate and permeate outlet. The retentate is the high-pressure outlet that contains species that diffuse slowly over the membrane. The permeate is the low-pressure outlet that is enriched with species that diffuse quicker over the membrane. The permeate outlet is on the same side as the feed inlet. We balance methane, CO2, nitrogen and oxygen. The membrane module has a dimensionless spatial coordinate Z. We set Z to 0 at the retentate outlet of the module. It is 1 at the inlet. Anywhere along the membrane, we can balance over an incremental part delta Z. The flow over the membrane of a species IN.I star is the length of delta Z times the permeance of the species Q times the partial pressure difference. The partial pressure difference is retentate pressure times retentate concentration X minus permeate pressure times permeate concentration Y. The concentrations X and Y are calculated from the molar flows of retentate and permeate. They are the molar flow of species I, divided by the sum of all molar flows at the coordinate Z. At any point along the membrane, we can express the permeate molar flow as the local retentate flow minus the retentate outlet flow at Z equals 0. Combining a Taylor linearization around an infinitesimal length delta Z with the definition of the flow over the membrane, N.I star, substituting the permeate flow and describing all concentrations with the local retentate flow gives the following differential equation. It is a boundary value problem. This figure shows the relative permeance of methane, CO2, oxygen and nitrogen of a commercial membrane for biogas separation as a function of temperature. CO2 has the highest permeance, followed by oxygen and then nitrogen and methane. The last two have low permeances. The permeance of membranes is temperature dependent. The higher the temperature, the higher the permeance and the fast molecules diffuse over the membrane. The temperature impact on permeances can be described with the Arrhenius equation. When it comes to biogas separation, the permeance of methane increases faster with temperature than that of CO2. The ratio of the CO2 and CH4 permeance is the selectivity alpha. The selectivity of a membrane drops with increasing temperature. This makes the inlet temperature of the membrane an important optimization parameter. The CO2, CH4 selectivity of commercial biogas membranes is between 40 and 50 at 25 degrees Celsius. We will later investigate the impact of selectivity on the biogas purification process. Selectivity is one performance indicator. The other indicator is the so-called capacity or productivity. It is the CO2 permeance multiplied with the area of the membrane module. Permeances of membranes are often not given in SI units but in GPU, gas permeation units, which is milliliters per square centimeter, second in centimeter mercury column. So, capacities have the unit GPU times square meter, or mole per second, and Pascal in SI units. The common process for the purification of biogas to biomethane and off-gas is the three-stage process. Biomethane is the CH4 enriched stream, and off-gas is the CO2 enriched stream. Raw biogas is mixed with two recycle streams and compressed to around 12 to 16 bar gauge. After compression, it is cooled to around 4 degrees Celsius to remove most water and reheated to at least 10 to 15 degrees Celsius above the dew point. The first membrane stage separates the biogas stream into a CH4 enriched stream with around 80% methane and a CO2 enriched stream with around 90% CO2. The second stage purifies the retentate of the first stage. Its retentate outlet is the biomethane, which contains around 1.5% CO2. The pressure of the second stage retentate, and indirectly the pressure of the first stage retentate and biogas compressor, is controlled with a pressure control valve in the outlet of the second stage retentate. The position of this valve impacts the purity of the produced biomethane. The permeate of the second stage is one of the recycle streams and is mixed with the incoming biogas. The permeate of the first stage flows to the third stage. The permeate of the third stage is the CO2-rich off-gas stream that is vented to the atmosphere or sent to a CO2 liquefaction plant. Modern membrane-based biogas upgraders can achieve 0.5% methane in the off-gas. The retented outlet pressure of the third stage is controlled with a pressure control valve. This valve controls the purity of the produced off-gas. After the expansion, the third stage retentate flows back to the inlet of the biogas compressor. The process has several independent variables that define the quality of the produced gases and the power uptake of the unit. These variables are the number of membrane modules in the first, second, and third stage, the inlet temperatures of each stage, and the retentate pressures of the second and third stage controlled by the respective valves. Another independent variable is the speed of the compressor, but we use this variable to control the biogas inlet volume flow to a constant value. In total, we have 8 independent variables. The vector Xi comprises all independent variables. To calculate all flows in the membrane upgrader, we need to solve the 12 boundary value problems, 4 species in 3 stages. The boundary values are as follows. When Z equals 0, the retentate flow of species I is equal to the outlet retentate flow of species I, which is denoted by the index omega. When Z is 1, at the inlet of each stage, the boundary values are as follows. For stage 1, it is the biogas feed stream plus the first stage minus the second stage plus the third stage retentate outlet. For stage 2, it is the retentate outlet of stage 1. And for stage 3, it is the feed minus the second plus the third stage retentate outlet. This allows to express all boundary values with the respective outlet flows of each stage for each species. Further, we assume isobaric and isothermal conditions along the membrane, so no pressure drop and no Joule-Thomson effect. We can now solve the boundary value problem to get all flows and compositions for a defined inlet flow and a set of parameters Xi. The figure on the right shows the flow of all 4 components along the dimensionless length of each stage. If we choose an arbitrary set of parameters Xi, the chances are quite high that the produced biomethane and off-gas do not have the target composition. Let's aim for 1.5% CO2 in the biomethane and 1% CH4 in the off-gas. 8 parameters can be manipulated to control 2 outlet values. Mathematically, the problem is underdetermined. We only need 2 independent variables to control the 2 outlet parameters. The remaining 6 variables can be used to minimize the power uptake or solve another optimization problem. We will introduce another constraint that the total number of membranes is constant. We want to find a set of parameters that ensures that the quality of the produced biomethane and off-gas are met while minimizing the power demand of the biogas upgrader. The power demand of the biogas upgrader depends on its throughput and outlet pressure. It is our cost function. We want to minimize the cost function P of Xi so that the parameters stay within their bounds. Xi min is smaller or equal to Xi is smaller or equal to Xi max, under the equality constraints that the total membrane area is constant. N1 plus N2 plus N3 equals N total, and that the CO2 content in the product gas and the CH4 content of the off-gas stay at their target values. I used the gradient-based MATLAB optimiser fmincon with a sequential quadratic programming algorithm. One of the tricks required to solve this problem is to find an existing non-optimal solution, which is stored as a mesh in the boundary value solver and then apply only small changes to the existing solution to find the optimum. So, a gradient-based optimizer is preferable for this application, even though it might not find the global optimum. The figures on the right show how the optimization solver finds the optimal set of parameter Xi that minimizes the cost function while maintaining all constraints and bounds. The upper left figure shows the constraint violation for the gas qualities in % on the left ordinate and the power uptake of the unit on the right ordinate. The abscissor shows the iteration number. It takes 41 iterations to find the optimum starting with the initial guess. The initial guess did not meet the constraints. The lower left figure shows the absolute pressures in the first stage retentate and permeate. The upper right figure shows the inlet temperature of each stage. The optimal solution has a maximal temperature in the third stage, the temperature has reached its upper bound, a minimal temperature in the first stage, at the lower bound, and a temperature somewhere half between minimal and maximal temperature for the second stage. The lower right figure shows the membrane area per stage. For the optimal solution, the first and third stage have about the same area, and the second stage is around half the size of the first or third stage. In the first 6 iterations, the optimizer brings the constraint violations to 0. This goes hand in hand with an increase of the cost function. The first noticeable improvement of the power uptake happens around iteration 14 when the first stage temperature reaches its lower bound. At integration 28, the third stage temperature reaches its upper bound. After that, the improvements to the cost function are only marginal. Let's have a look at the optimal solution. The inlet flow is 1,627 norm cubic meters per hour biogas with a methane content of 50%, a nitrogen content of 0.3%, and an O2 content of 0.5%. The rest is CO2. The stream is set to 100%. The inlet pressure is 1 bar. All pressures here are given as absolute pressures. The biogas stream is mixed with 2 recycle streams, a 20% stream from the second stage permeate and a 4% stream from the third stage retentate. The mix is compressed to 18.3 bar. The flow through the compressor is 124% of the biogas stream. The number is called the recycle ratio and should be kept at around 130% in biogas upgraders. After compression, the gas is cooled to 10 degrees Celsius. 35.5% of the total membrane surface are allocated to the first stage. The retentate of the first stage is 71% of the biogas flow and flows to the second stage. It is heated to 37 degrees Celsius. 26.4% of the total membrane area are allocated to the second stage. The retentate of the second stage contains 1.5% CO2 as the constraint requires. The O2 content in the biomethane is around the same as in the incoming biogas and outgoing off-gas, 0.5%. Some of the O2 can permeate through the membrane. Nitrogen accumulates in the product gas. It has a low permeance and a low partial pressure, so it stays on the high pressure side of the membrane. The outgoing biomethane stream is 51% of the ingoing biogas stream. The permeate of the first stage is around 53% of the biogas stream. It is heated to 60 degrees Celsius before entering the third stage. 38.1% of the total membrane area are allocated to the third stage. The pressure from the first stage permeate outlet through the third stage to the pressure control valve is 3.41 bar. The third stage permeate is 49% of the incoming biogas stream and contains 1% methane as required by the constraint. In this example, the volume flow is quite high compared to the available membrane area. The optimal parameter vector Xi depends on the biogas composition, target gas qualities, total membrane area, and other process modifications. The optimum shown here is for one set of parameters. It will vary with different total membrane areas and required gas qualities. The FMIN consolver only finds local optima, other global optima could be out there. But now that we have the model, we can run a couple of sensitivity studies to see the impact of total membrane area, target gas qualities, and other process modifications. First, we investigate the impact of the total membrane area. The upper left figure shows the total power uptake of the compressor in kilowatts as a function of total membrane area in square meters. I ran the optimization for 2 scenarios. First, a flexible distribution of the membrane area, shown as a bold line, and then for a fixed allocation of the membrane area in a 1:1:1 ratio as a dashed line. There is very little difference between the optima, which means that the impact of the allocation of membranes to each stage is often overestimated. A simple 1:1:1 allocation is good enough. As expected, the total power demand decreases when the available surface increases. Interestingly, commercial membrane-based biogas upgraders often shut off membrane surface in partial operation. The upper right figure shows the first stage retentate and permeate pressure as a function of total membrane surface. Both pressures decrease when the total membrane area increases. So, commercial membrane upgraders do not reduce pressure in partial operation, but close off membrane area. The lower left figure shows the inlet temperatures of the 3 stages. We can see a general trend that the first stage should operate as cold as possible, except for very low total membrane areas, and the third stage should operate as hot as possible, except for very large membrane surface. In other words, the first stage should operate at maximal selectivity and the third stage at maximal capacity. This has implications on the plant commissioning. When the plant is initially stacked with fresh membrane modules, put the most selective modules into the first stage and the least selective ones into the third stage. All modules are tested in the workshop before installation, and the selectivity of each module is certified, so they can be strategically allocated. The last figure shows the recycle ratio as a function of total membrane surface. The higher the total membrane surface, the higher the recycle ratio, and the lower the pressure under optimal conditions. But even with reduced pressure, more CH4 will diffuse over the membrane at increased membrane surfaces, increasing the recycle streams as a result. Next, we are going to investigate the effects of permeate recompression. The separation efficiency of a membrane depends on the pressure ratio of retentate and permeate. It does not depend on the absolute pressure difference over the membrane, but on the pressure ratio. Let's assume we have a retentate pressure of 10 bar and a permeate pressure of 1 bar. The pressure ratio is 10. If we apply a vacuum on the permeate side and lower the pressure to 0.5 bar, the pressure ratio doubles to 20. This leads to a significant improved CO2 recovery and permeate purity. The effect is not the same as increasing the retentate pressure to 10.5 bar. We can try to improve the process by installing permeate compressors on all 3 stages. The most common application is a vacuum pump or exhauster in the second stage permeate, here indicated in blue. Typically, it creates a mild vacuum of several hundred millibar on the second stage permeate side. A blower can also be installed in the first stage permeate, here highlighted in red. It operates under positive pressure and increases the feed and retentate pressure of the third stage compared to the permeate pressure of the first stage. Sometimes blowers are installed in the third stage permeate outlet, here highlighted in green. All of these blowers will require energy to operate, and their energy requirement must be added to the cost function of the optimization. We can now run the optimizer for various inlet to outlet pressure ratios for all 3 locations and plot the power demand under optimal conditions. The result is shown here. The highest reduction in power uptake can be achieved with a recompression of the first stage permeate. A vacuum blower at the second stage permeate outlet also results in a slight improvement of the power uptake. Installing a vacuum blower in the third stage does not lead to an improvement of the power uptake. In fact, it increases the power demand of the plant. How to interpret these results? First, we notice that the energy savings are only marginal, 2 to 3% at best. The best solution, a blower in the first stage permeate, must compress 53% of the biogas stream, whereas a vacuum blower in the second stage must only compress 20% of the biogas flow. It will be cheaper. Also, it must not be pressure rated as it operates under vacuum and not at 3 to 4 bar. The reason for the vacuum blower in the second stage is often process control rather than energy improvement. The vacuum blower can control the product gas quality very well. I have seen several plants with a blower at the third stage permeate outlet. Often this is to overcome CO2 accumulation around the off-gas stack. CO2 is heavier than air and will sink to the ground in a wind-still environment, or if the stack is near a high building or noise abatement wall. The blower is a futile attempt to push the off-gas out. But the off-gas volume flow is defined by the biogas inlet flow. The outlet pressure of the stack is ambient pressure. Neither flow nor pressure at the end of the stack can be manipulated with an inline blower. The correct installation of this blower is to suck in air from the environment and commingle it with the off-gas before it is expelled from the stack. This increases the velocity in the stack and premixes the CO2 with air, which lowers the density of the expelled gas. The installation of an additional blower might improve the performance of the plant, but it adds another process unit that can break. From the operational point of view, I would rather add more membrane modules than an additional process unit to save on power demand. Next, we investigate the impact of gas qualities on the optimal operation of the biogas upgrader. First, I increase the methane content of the biogas from 50% in 5% steps to 70%. The power uptake per cubic meter of processed biogas increases, whereas the power demand per cubic meter of produced biomethane decreases. This is not intuitive. When the incoming biogas has less CO2, it requires more energy to clean up the gas. The reason for this is an increased recycle ratio with increased methane content of the incoming biogas. When we increase the target CO2 content in the product gas, the power uptake drops as expected. The recycle ratio stays more or less constant. Instead, the compressor pressure drops with more CO2 in the product gas. When the methane content in the off-gas is varied, the power demand and recycle ratio vary as well. When the methane drops from 1% to 0.5%, the power demand and the recycle ratio increase. However, increasing the methane target in the off-gas from 1% to 1.5% does not lead to a significant drop in power demand or recycle ratio. Lastly, we investigate the impact of the membrane selectivity on the plant performance. I increase the selectivity by decreasing the permeance of methane and keeping the permeance of CO2 constant, so it does not affect the capacity of the membrane module. The selectivity increases from 100 to 125 to 150%, and I investigate 2 scenarios. A low and high total membrane area with 90 and 270 membrane modules in total. The low total membrane area scenario is in bold lines, the high area scenario in dashed lines. With increasing selectivity, the power uptake of the plant drops. With a low total membrane area, the recycle ratio stays constant, but with a higher total membrane area and subsequent higher recycle ratio, an increase of selectivity leads to a decrease in the recycle ratio. The pressures are relatively unaffected by the change in selectivity and are not shown. At a higher selectivity, the membranes operate at elevated temperatures, which offsets part of the selectivity gains. But the overall effect of an increased selectivity is only marginal. A 50% increased selectivity leads to a power saving of just 4%. Keep this in mind when comparing proposals from different OEMs. A slightly reduced selectivity can simply be offset by installing more membranes in the first place. Before I conclude, I want to quickly discuss the advantages and fallibilities of membrane-based biogas upgraders. Let's start with their properties. Membrane upgraders are probably the most common biogas upgrader technology in the UK. They operate continuously. The upgrader units are usually split into a compressor section, which compresses, dries, and filters the incoming biogas, and a membrane container section that contains the pipework, membranes, valves, and sensors. Compressors are mostly oil-lubricated screw compressors with extensive oil removal technology downstream, though some older membrane upgraders use reciprocating piston compressors. Some heat from the compressors is recovered to heat up gas streams in the biogas upgrader, especially before the first stage. Now let's invert the problem. How can we break a membrane-based biogas upgrader? Membrane upgraders are sensitive to 6 types of contamination: water, ammonia, VOC, H2S, siloxanes, and carbon dust. When an upgrader shows a deteriorating performance, it is almost always because of one of the 6 reasons. We start with water. During operation, membrane cartridges cool down because of the Joule-Thomson effect. When CO2 permeates through the membrane and is expanded, it cools down by around 0.7 degrees Celsius per bar. For methane, the value is 0.5 degrees Celsius per bar. If the dew point of the gas entering the membrane is not sufficiently apart from the gas temperature, condensation can occur on the membranes, which can damage the membrane fibers mechanically. Chillers fail frequently, and a non-functioning chiller will not lead to immediate problems with the biogas upgrading unit, so the operator might ignore the failure and continue to run the plant without it, causing condensation on the membranes. Another way of damaging the membrane with water is a blockage of the condensate removal points of the main chiller downstream of the biogas compressor. Water can also be introduced via heat exchanger leaks. Ammonia can damage the material of the membrane, especially when it appears alongside water condensation. The best indicator for ammonia in the biogas is the pH of the digester. If it is above 8, the biogas almost certainly will contain more ammonia than allowed by the OEM. Ammonia can be easily removed from the biogas with a simple water scrubbing step. The water scrubbing can be combined with the drying step of the biogas before it enters the biogas upgrader. But without a scrubber and with a high pH in the digester, the membranes will be contaminated with ammonia over time. Volatile organic compounds, or VOC, will block the membranes. They create an additional layer on the membrane fiber, creating a thicker layer for the CO2 to diffuse through. Relevant VOCs can be roughly split into 3 groups. Small molecules like acetone, methyl ethyl ketone, butanol are created in fermentation reactions, often at lower pH and high temperatures, for example in hydrolysis tanks. Terpenes like limonene and pinene are created in food and green waste fermentation. Aromatic hydrocarbons like BTX are breakdown products of amino acids and can be found in the biogas of plants that have a protein-rich diet. Most AD plants do not measure VOCs on a regular basis in the biogas, but recently online VOC analyzers have been introduced that can also measure ammonia. They are recommended for waste fermentations or larger AD plants in general. H2S is a known impurity of biogas. While it will not necessarily damage the membrane, it will break through into the biomethane and can cause gas quality issues shutting down the upgrader. Typically, H2S is removed with an activated carbon filter. Siloxanes are present in sewage sludge and waste fermentations, but were also reported in fermentation of grass silage. They originate from silicone-based products like shampoo, detergents, and paper coatings, and are a frequent contaminant in landfill gases, but rare in energy crop, agricultural waste, and food waste digestions. Siloxanes are difficult to monitor online and to remove. Landfill plants use special temperature swing adsorption processes to capture siloxanes, but these processes require heat for the regeneration of the adsorber beds. Most AED plants will not require a designated siloxane removal step unless they feed special feedstocks. The last contaminant is carbon dust. All compressors, Even oil-free reciprocating compressors leak some oil droplets and oil vapor into the biogas and require an oil removal step with a small activated carbon filtration. Downstream of the oil removal carbon should be dust filters to capture carbon dust. When the biogas upgrader experiences an emergency shutdown, it can quickly depressurize, which can lead to the fluidization of the carbon filter and to pressure surges that can propel carbon dust through the header system. Eventually, the carbon dust ends on the potting resin and blocks the inlet to the hollow fibers. The different types of contaminations can damage a membrane in two different ways. It can lead to a loss of capacity or a loss of selectivity. A loss of capacity means that the membrane is still intact, but CO2 diffuses slower through it. When this is the case, the pressure in the system increases and the recycle ratio increases. In uncontrolled systems, the gas qualities will deteriorate. Contaminations with VOC and carbon dust lead to a loss of capacity. A loss of selectivity happens when the membrane breaks and gas flows indiscriminately from the high to the low pressure side. Water contaminations are typical causes for a loss of selectivity. A loss of selectivity will lead to a substantial change in the pressures in the system. If membrane modules can be valved off individually, shutting off a membrane which experienced a loss of selectivity will lead to an instantaneous change of the pressures in the system. I highlighted all the ways a membrane-based biogas upgrader can fail, but if membrane biogas upgraders are maintained correctly and all contaminants are removed before the biogas enters the first membrane stage, membrane upgraders cause few problems and are very reliable. Let's summarize. I explained the mass balance around a countercurrent membrane module for a multi-component mixture of ideal gases. The system requires solving a boundary value problem, one equation per species and stage. In total 12 equations for a 4-component 3-stage system. The permeance is temperature dependent. The higher the temperature, the higher the permeance, but the permeance of methane increases faster with temperature than the permeance of CO2. The ratio of the permeances of CO2 to CH4 is the CO2, CH4 selectivity. It drops with increasing temperature. For commercial gas permeation modules in AD, the selectivity is between 40 and 50 at 25 degrees Celsius. The capacity of a membrane module is the product of CO2 permeance and active surface area. I introduced the 3-stage process for the purification of biogas and its independent variables. They are the temperatures and membrane area of each stage and the retented pressures of the 2nd and 3rd stage. We can input the results of the boundary value solver into a gradient-based optimizer to find the optimal set of parameters that meet all the constraints and bounds and minimize the power uptake of the plant for a fixed biogas input. I showed the flows and composition of all streams for an optimal solution. Increasing the total membrane area leads to a reduced power demand, reduced pressures, and increased recycle ratio. The temperatures are the most important optimization parameters. Under optimal conditions, the 1st stage operates as cold as possible, at maximal selectivity, while the 3rd stage operates as hot as possible at maximal capacity. Allocating the membranes in a fixed 1:1:1 ratio to the stages has no material disadvantage to an optimized membrane distribution. Permeate recompression in the 1st and 2nd stage can lead to a slight improvement of the power uptake, but the preferable solution is to install more membranes and omit the additional process unit. Variations of the input and target output gas qualities impact the power demand and recycle ratio of the plant. Increasing the methane content of the biogas leads to a higher power demand per cubic meter biogas processed, but to a lower power demand per cubic meter biomethane produced. A lower CO2 content in the product gas leads to a lower pressure and power demand at constant recycle ratio. A higher methane slip over 1% does not lead to a lower power uptake, but lowering the CH4 slip results in a higher power demand. Increasing the selectivity further does not lead to a significant improvement of the upgrading process. If the system must be improved, add more capacity. Lastly, I discussed the 6 ways a membrane-based biogas upgrader can fail. These are contaminations by water, ammonia, VOC, H2S, siloxanes, and carbon dust. Gas permeation biogas upgraders are highly reliable if the compressor and chiller are well maintained and impurities are prevented from reaching the 1st stage. This concludes the presentation about optimizing membrane-based 3-stage biogas upgraders. I hope you learned something new, and I see you in the next episode of Biogas Basics.